This segment we're going to learn how to use the psychrometric charts. So the psychrometric charts are just a graphical representation of important properties of atmospheric or moist air. And the charts that you have are only valid at 1 ATM. So it's very important to remember. So you have these in English units as well, still only valid at 1 ATM. If you ended up working at an elevation that was higher or lower, then you would probably have psychrometric charts that were at an appropriate atmospheric pressure as well. So, but the ones that you have are only valid for 1 ATM, so they're only useful if you're looking at a process for atmospheric air in which the process is occurring at 1 ATM. Okay, so without further ado, let's see what things that we can get off this chart. So we can get the specific humidity or the humidity ratio, and that's on your on the y-axis there. So if I'm anywhere along that red line right there, it looks like I would have a specific humidity of 0.016 kilograms of water per kilogram of dry air. I can also get the relative humidity. So these are those kind of curved lines. You see at the very bottom, you've got a relative humidity of 10%. The red line is at a relative humidity of 20%. And then you've got 30, 40, 50, 60, 70, 80, 90. And then that very top line, the top line is corresponding, or the top curve, I guess, is the one that corresponds to a relative humidity of 100%. All right, so you can also graph what's called the dry bulb temperature, and the dry bulb temperature is what you think of when you think of temperature. If you're given a temperature, it's the dry bulb temperature. It's what a regular thermometer is measuring. So this is on the x-axis, so if I'm anywhere along that red line here, my dry bulb temperature is 10 degrees Celsius, so pretty simple. My wet bulb temperature is on there as well, and this is measured kind of the same way. You've got a regular thermometer, except you've got a wick gauze that's saturated with water. And so what happens is if the air between the wick and the gauze, or between the wick and the thermometer itself, if that atmospheric air is not fully saturated with water, then water evaporates out of that wick and sort of joins, I guess is another way of saying it, joins the atmospheric air between the wick and the thermometer. And so as that happens, the air is cooled by evaporative cooling, and so the temperature that is measured is lower, or lower than the dry bulb temperature. So the wet bulb temperature, in effect, is the lowest possible temperature that can be achieved through evaporative cooling alone. Okay, so let's see on our chart here. So the line here, anywhere along that red line, your wet bulb temperature is 10 degrees Celsius. So the numbers corresponding to the wet bulb temperature, these are the ones to the left of the line that corresponds to 100% relative humidity. So 10 degrees Celsius for my wet bulb temperature. Let's look at another location. So here, this is between 10 and 20, or the lines that are labeled 10 and 20. So you can kind of count up that this would be at 14 degrees Celsius. So you'd have a wet bulb temperature of 14 degrees Celsius if you're anywhere along that red line there. All right. One side note here. So if your atmospheric air is fully saturated so that no further evaporation of water from that wick can occur, that would be the case if your relative humidity was 100%. So say I'm like right there on that relative humidity line of 100%. So I've drawn a dot there corresponding to my state. And if I looked at the wet bulb temperature, that would be 14 degrees Celsius, but my dry bulb temperature would be the same, right? Because the temperature is not changing the way that I'm measuring it here. The temperature wouldn't decrease due to evaporative cooling because there is no evaporation of the water within that wick into the atmospheric air. So if your relative humidity is 100%, your wet bulb temperature and your dry bulb temperature are going to be exactly the same. All right, another property that you can get is the specific volume of the dry air. So that's in units of meters cubed per kilogram of dry air. So if I'm along this red line here, it looks like I'm between the specific volume lines that are explicitly labeled at 0.8 and 0.85. So if I kind of count up, I'm right at about 0.84 meters cubed per kilogram of dry air. The other property that I can get is what's called the specific enthalpy of the moist air. If you notice the units, this is in kilojoules per kilogram of dry air. So we're still talking about atmospheric air, which is a mixture. You've got two components. You've got dry air and you've got water vapor. So I can calculate the enthalpy based upon those two components. And if I divide through by the mass of the air, that would give me the units of kilojoules per kilogram dry air. So you see HA has nothing in front of it. HV has this MV over MA, and you may recognize that as just the definition for the specific humidity or the humidity ratio. So that's what we're talking about. That's the specific enthalpy of the moist air. And you'll see as we go through air conditioning processes why this term right here is very useful. All right, so if I'm right on this line right here, and I follow all the way up, you can see that my specific enthalpy is measured as 30 kilojoules per kilogram of dry air. So the lines of specific enthalpy and wet bulb temperature, they're parallel to one another. So you want to make sure that you're reading the specific enthalpy values. Those are all the way to the left, the leftmost values. So this is 30 kilojoules per kilogram of dry air. If I'm anywhere along that line, let's say I'm up here instead, looks like I would be about 50 kilojoules per kilogram of dry air. All right, so let's work a problem. Let's say that we have atmospheric air at 30 degrees Celsius and 40% relative humidity, and we want to find all the other properties that we could possibly find on that psychrometric chart. So the temperature is 30 degrees Celsius, and that's my dry bulb temperature. So if you're given a temperature, it's the dry bulb temperature. If you're given a wet bulb temperature, it'll explicitly say the wet bulb temperature is this. So if you're just given temperature, it's dry bulb temperature. So 30 degrees Celsius, relative humidity of 40%. So what I have to do is to just have to draw a dot at my location, at my state of the atmospheric air on this psychrometric chart. So I've got a line corresponding to a relative humidity of 40%. I've got a line corresponding to a dry bulb temperature of 30 degrees Celsius. And where those guys come together, that's the state of my atmospheric air. So there's my little dot. And I'm just gonna keep my dot there. So let's see what I can find. Well, I can find my humidity ratio, or the specific humidity, and it looks like it's about 0.011. As long as you're close, that's fine. I mean, there is some amount of error involved in reading these charts, so as long as you're pretty close, that's fine with me. The other thing that I can get, let's see, I can get my specific volume of the dry air. So it looks like if I look at the lines for the specific volume that are explicitly labeled, there's one for 0.85, there's one for 0.9. So if I count up from the 0.85 line, I got 0.85, 0.86, 0.87, and it looks like I'm between 0.87 and 0.88. So I'm just going to say it's about 0.875. Once again, you're just you're estimating it. You're just reading a chart. So, all right, so I've got my specific volume. The other thing I can get my specific enthalpy of the moist air, and it looks like it's about 57. And while I have the line drawn in that direction, I'm also going to read off the wet bulb temperature, which looks like it's at 20 degrees Celsius. And I guess, yeah, that's it. That's all the things that I need. So, all right, well, we'll work some problems the next time that we meet. Thank you for watching.